This is a basic college level oceanography sediment lab. So you guys will enjoy it. It's pretty fun. No, you don't get to play with sediments, but it's still a cool lab. So let's go through it. On the first page, it gives you classification of marine sediments. We've gone through all those. If you notice on number 1, there's a new word there. Terrigenous. It's the same thing as lithogenous. They both mean the same thing. So if you think of terrigenous, terrestrial means land. So it's just another way of saying lithogenous. So you're going to see it both ways. So when you see the word terrigenous, it just means the same as lithogenous. So it gives a brief description. So I'm going to jump down to right under number 4. So what I want you to do is on your sheet, I want you to point your finger to where I'm about to talk, which is right under number 4 to let me know that you guys are in the correct spot. And I'm going to read. So please listen and follow along as I read. Are we good? You all there? Yep. All right. By weight and volume, the first 2 categories above account for the vast majority of ocean bottom sediments. Terrigenous and biogenous sediments are the subject of this lab. We're not really going to spend much time talking about hydrogenous or cosmogenous. The following sections provide some additional background details on the 2 sediment classes. So terrigenous sediments. Terrigenous sediments are usually subclassified by either grain size or mineral type or both. If you look at Table 1, which is on the next page, it shows the standard grain size classification scheme, the Wentworth scale. So if you look at the Wentworth scale, it's on page 2. That is how they classify grain sizes. So if you've never known what the difference between a pebble and a boulder is, there's actually a difference. And Mr. Miller, where did you put the ruler? Thought you put it in here.
Right there.
Oh, it's just blue, so I see through it. Now, where did you put the rock? All right, let's use this one. Okay, with this rock, do you think, looking at this scale here, do you think this rock is going to be a boulder, a cobble, a pebble, or a granule? How many people think it's going to be a boulder? Raise your hand. Cobble. Pebble. Granule. Sand. Clay. Silt. All right. So what you do is you take the diameter. You take the diameter of the longer side, not the small side, the longer side, to figure out what it is. So we look, and if you see, it says for a boulder it has to be greater than 256 millimeters, which is 26.5 centimeters. Does this look greater than this? This is roughly 30 centimeters. So if I take this, take the longest section, I have approximately 16 centimeters. How many millimeters is that? Multiply it by 10. 160. So we have 160 millimeters. So which category would it fall into? Cobble. This is a cobble. So the classification of this rock would be a cobble. How about this rock? Think this is a boulder?
Yeah.
So let's take it. It is approximately 4.5. So that's 45 millimeters. It is a pebble. So that's how you figure out what rocks are. Rocks have different classifications. So now you know how to tell the difference between a pebble, sand, and a boulder. All right. So as might be expected, so I'm right below the table. As might be expected, larger grained, heavier terrigenous particles settle to the bottom first. They're heavy. They sink right away. Therefore, they're concentrated to the closest of the source land. So who here has been swimming in a lake at some point? Okay. If you go into a lake, are there a lot of big rocks in the middle of the lake? No. Generally, no, not unless someone's throwing them in there. Why? What happens to rocks as they enter the water? They sink right away. So where are all the rocks going to be? They're going to all be on the outside. Same thing with the ocean. All the big rocks are going to be on the outside because they sink right away. They don't make their way to the center of the ocean unless someone puts them there, or unless they break off of the plate. All right, finer grained, lighter particles like silts and clays remain suspended in the seawater for a longer period of time, sometimes months or years, and therefore can settle to the ocean bottom at a much greater distance from the continents. So if we look, if you go out in the middle of the lake and you feel the ground, a lot of it's like this dirt, sediment type stuff, and you pull it up and it's mucky. That's clay and dead organic material. It's because the clay can be in the water for a long period of time. Same with the ocean. This differential in settling according to the particle size provides a natural sorting mechanism for terrigenous sediments dependent upon the distance of the continental source. All right. So I'm going to let you guys read the rest on your own. So we're going to jump down to the second paragraph on page 3, where it starts out with siliceous oozes. Siliceous oozes. I want you to put a little star next to it. The answer to question number 2 is somewhere in that paragraph. I repeat, the answer to question number 2 is somewhere in that paragraph, and it's up to you to find it. Otherwise, the answer to number 2 is also in your notes. We talked about it yesterday. All right, so if you go down, there's some methods how they sample sediment. We talked about it when we talked about the notes with the big ship who drills down. So turn the page. Number 4 is a puzzle. You have to figure out what it's trying to tell you. It's blank. There's nothing on there. Page 5. Go to page 5. If you look at page 5, it's a list of your core samples. So on the left, it gives you the core number, 1 through 16. So there's 16 core samples that were taken. Right next to it is a description of what's in that core sample. So if I look at core sample 1, it contains fragments of volcanic rock and a small amount of ooze. And then if you jump over one more, it gives you the percent of calcium chloride, or calcium carbonate, in the top 10 centimeters of that sample. Now if there's a dashed line, it means that they could not find any calcium carbonate in that sample. So what would our number be? Probably 0. And then on the far right, it gives the depth at which the sample was taken. All right, we good there? So let's turn our page. By the way, this is table 3.2. All right. So on this page, we have a map. I want you to point to the upper left-hand corner of the map. Point to the upper left-hand corner of the map right now, please. Go down about an inch. What do you notice? Numbers. Those are depths. They end with an M. That means meters. Go down a little bit more. You see single-digit numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then you cross the mountain range and you have 10, 11, 12, 13, 14, 15, 16. You good? Those are where the core samples were taken from. So where the 1 is, that's where core sample 1 was taken from, and so forth. So if you jump down to the bottom of the map, what do you see written down there? I see Ocean A and Ocean B. Who else sees that? Yep. Everybody see that? So if I was to look at core samples 1 through 9, do you think those would be in Ocean A or Ocean B? Ocean A. How about 10 through 16? Ocean B. Good. Let's jump down to number 1. Using data from 3.2, plot the percentage of calcium carbonate. So we want to know just calcium carbonate right now versus depth. So we want to compare the amount of calcium in the sediment versus the depth at which it was taken. So we're going to plot that. You're going to plot them all except for the ones that have a dashed line, because obviously don't have any calcium carbonate in them. In the graph below, label each point with a sample number and note whether it came from Ocean A or Ocean B. So someone tell me, sample 1, is there any calcium carbonate? No. So do we need to plot it? No. All right, let's go down to number 2. Number 2, how much calcium carbonate was in that sample? 90%. What was the depth of that sample?
2,000 feet.
So find,
At this time, all students are required to be in class.
so find where it says 2,000 for depth and go over to where it says 90% for the amount of calcium carbonate and put a little dot. Then next to that dot, write the core sample. What core sample is this? Number 2. And then write what ocean you found this core sample in. A. So you'd write 2-A. 2 core sample dash A. Yep. By the little dot. All right, I want you to do the next one on your own really fast. You got 30 seconds. Let's go. I want to see that you know how to do this. So do the next one on your own really quick.
Good.
Do the next one on your own really fast. Nice.
Did we just do 2?
You're doing number 3 now. Core sample 3.
How do we know what
Which what?
By the number. If it's a little number, then under 9. You want us to just keep doing them?
So find it and then go down and see where it is.
75%.
I was at court.
Okay. Okay. It looks like everybody's pretty good. Are there any questions on how to plot these right now? Okay. Turn the page, please. Number 2. Remember where you can find the answer to number 2. So later on, you're going to go back and answer that. Jump down to number 3. Everybody on number 3? All right, 3A. Using table 3.2 and figure 3-2, plot a depth profile of each line of cores 1 through 9 in Ocean A. So we have Ocean A on this side, 1 through 9. If you notice, there is a 1 through 9 on the top. And then 10 through 16 in Ocean B. Are we good there? Okay. For each, now part B, so this is the second part, so that was the first part. Part B is you're going to color code each of those points based on what material is in the core sample. Where would you look to figure out what was in each core sample?
That one page that has
That table that gave a list of the description. All right. So it says, for each depth point plotted, use color pencils to draw a colored circle or multiple circles, because some have more than one thing in them, around each point to indicate the main types of sediment found in the core at the bottom. Use red for clays. All clays are red. Blue for oozes, yellow for gravel, sand or silt, and black for volcanic rock or basalt. You will use this graph to help you answer further questions. There are color pencils up here. So how about we do the first one together? So plot point A on your graph really quick. Or plot site or core sample 1. So find the 1 and then coordinate with the depth. All right, so your point should be approximately right here. Under number 1, and then under 1,500 meters, you would have a point. Now, what color would we circle that point with? What colors or color?
blue.
Blue and why?
Because it has
Because there's ooze in it, and blue is ooze, and then what other color? Black, because there's volcanic rock. Good. So you're going to do that for all 16 points.
Do we circle around it or?
You can circle around it, yeah. All right, turn the page. Well, you're going to circle it with the colors that it represent. 5, 6, 7, 8, and 9. You're just going to complete with your partner. Number 9, make sure you actually read the question because you're going to have to calculate, and it gives you the information to calculate it. Number 10 is extra credit. You're going to have to use all the knowledge that you learned to answer number 10. You will have today to do this, and you will have part of tomorrow to finish. Are there any questions? All right, you have the remainder of the class to work on this.
Yeah?